If A is diagonalizable, we need to find P such that P inverse AP is diagonal matrix, where this A matrix is given to us. We need to find such P matrix, right, such that P inverse AP is diagonal matrix. So the matrix A is given to us. To find that matrix P, we need to get first the eigenvalues of A, and corresponding to these eigenvalues we need to get the eigenvectors too, right? So let's find the eigenvalues of A first. For that we need to write the characteristic equation. So the characteristic equation of the matrix A is the determinant of lambda I minus A equals to 0, where this I is your identity matrix, the 3 by 3 identity matrix, because A is 3 by 3 matrix, right? So to find lambda I, we write lambda into the identity matrix, and that is equal to lambda 0 0 0 lambda 0 0 0 lambda, right? And now we need to subtract this A matrix from this lambda I. So what we get? We get this to be the determinant of, okay, so lambda minus 2, that is lambda minus 2, then 0 minus 2, that is minus 2, and then 0 minus 1, that is minus 1, and then likewise it is minus 1, then lambda minus 3, then minus 1, then minus 1, minus 2, and lambda minus 2, and is equal to 0. And now we need to get the determinant of this. So this is lambda minus 2 into, cross multiplying these two we get lambda minus 3 into lambda minus 2, minus 2 into minus 1, that is 2. So this becomes minus 2, then minus, writing this minus 2, that becomes plus 2, into, cross multiplying these two, this is 2 minus lambda, minus 1 into minus 1, that is 1. So this is 2 minus 1, that is 1, 1 minus lambda. And then minus 1 into, cross multiplying these two we get, so this is 2 minus 1 into lambda minus 3, that is minus of lambda minus 3, that becomes plus lambda minus 3. And this is 2 minus 3, that is minus 1, so this is lambda minus 1 equals to 0, right? We can also make this as lambda minus 1 by taking negative outside. So if I take negative outside, I get here also lambda minus 1, so that these two becomes common to each other. And solving this we get, this is lambda square minus 5 lambda plus 6 minus 2, and 6 minus 2 is 4, so this is 4. So let's write this. So this is lambda minus 2 into lambda square minus 5 lambda plus 4, and here if I take lambda minus 1 outside, we get minus 3 lambda minus 1. So this is minus 3 into lambda minus 1 equals to 0. And now we need to make the factors of this. So that is lambda minus 1 into lambda minus 4 minus 3 times lambda minus 1 equals to 0. And now let's take lambda minus 1 outside of these terms, and we get inside lambda minus 2 into lambda minus 4 minus 3 equals to 0. Solving this further, we get, this is lambda square minus 6 lambda plus 8 minus 3 equals to 0. 8 minus 3 is 5. Making the factors, we get lambda minus 1. Factorizing this, we get this to be lambda minus 1 into lambda minus 5 equals to 0. So we are getting lambda minus 1 whole square into lambda minus 5 equals to 0. So we are getting the values of lambda to be 1 and 5. Lambda equal to 1 is of multiplicity 2. Lambda equal to 5 is of multiplicity 1. Right? So we have got two eigenvalues. So writing this, the eigenvalues of A are lambda 1 equal to 1 of multiplicity 2, and lambda 2 equal to 5 of multiplicity 1. And corresponding to these eigenvalues, we need to find now the eigenvectors. Okay, when lambda 1 is equal to 1, for the first eigenvalue, we need to write the homogeneous equations for that. So that is lambda 1 I minus A x equal to 0. Right? To get this, we just need to put lambda 1 equal to 1 in place of lambda over here. Right? So that becomes 1 minus 2, that is minus 1 minus 2 minus 1. In the second row we get minus 1, then 1 minus 3, that is minus 2 minus 1. Similarly, in the third row we get minus 1 minus 2 minus 1. All the rows are same. So what are the homogeneous equations we get? So from here we get x1 plus 2x2 plus x3 equals to 0. Now because x1, x2, x3, the values are belonging to the set of the real numbers, right? So let's give value x3 to be equal to 0. You can also take x2 to be equal to 0, x1 to be equal to 0. Right now I'm taking x3 to be equal to 0. So from this equation I get x1 plus 2x2 equals to 0. That is x1 will be equal to minus 2x2. So for x3 equal to 0, I am getting x1 to be equal to minus 2x2. So that will be equal to minus 2 if I take x2 to be equal to t, where t belonging to the set of real numbers. So this is minus 2t. x1 is minus 2t. x2 is t, x1 is minus 2t, and x3 is 0. Right? This is the one way. Similarly, if I take x1 to be equal to 0, what I get from the same equation, if x1 is equal to 0, x3 to be equal to minus 2x2, right? x3 to be equal to minus 2x2. So if x2 is t, where t belonging to the set of real numbers, I get x3 to be equal to minus 2t. Very fine. For x2 equal to t, where t belonging to the set of real numbers. Right? So what are the vectors we are getting? So the eigenvector x1, x2, x3 is equal to, for the first condition, I have taken x3 to be 0, x2 is t, and x1 is minus 2t. Right? So this is equal to, taking t outside, I get minus 210. For t belonging to the set of real numbers. This is the first way to get the eigenvector. Because lambda 1 is equal to 1 is of multiplicity 2, I must have two eigenvectors. Therefore, I have also supposed the second case for taking x1 to be equal to 0. And the another eigenvector I get. For x1 to be 0, x2 is t and x3 is minus 2t. So that will be equal to t, and here 0, 1, minus 2. For t belonging to the set of real numbers. So we have got two eigenvectors which are linearly independent to each other. Right? We cannot write the first vector to be the scalar multiple of the another vector, which means these two vectors are linearly independent. Right? So writing this, so we have got x1 to be equal to minus 2, 1, 0 to be one vector, and x2 to be equal to 0, 1, minus 2, the another vector, which are linearly independent, right? Now the second case, eigenvalue 2 is equal to 5, and this eigenvalue is of multiplicity 1, so we need to get only one eigenvector, right? So writing the homogeneous equation, which is lambda 2I minus a into x equal to 0. So this time we need to put lambda 2 to be equal to 5 in place of this lambda. So 5 minus 2, that is 3. 3 minus 2 minus 1 to be the first row, minus 1, 2 minus 1 be the second row, minus 1 minus 2, 3 to be the third row. This is x1, x2, x3 and is equal to 0, 0, 0. What are the homogeneous equations we get? The first homogeneous equation is 3x1 minus 2x2 minus x3 equal to 0. Second one, minus x1 plus 2x2 minus x3 to be equal to 0. Third one, minus x1 minus 2x2 plus 3x3 to be equal to 0. All these equations are different. So if I subtract first two equations, I get 4x1 minus 4x2 to be equal to 0. That is x1 is equal to x2. And if I subtract second and third, I get 4x2 minus 4x3 to be equal to 0. That means x2 is also equal to x3, which means we get x1 to be equal to x2 to be equal to x3. All the three values are equal. Yes, if I give x3 to be equal to the value t, where t belonging to the set of real numbers, I will be getting x1 equal to x2 equal to x3 equal to t. All the values are equal to that t, right? So writing the eigenvector for this, I'm getting t, 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 right? If I take t outside, I get 1, 1, 1, where t belonging to the set of real numbers. So the eigenvector, so I'm taking the eigenvector to be the column vector 1, 1, 1, right? So writing this eigenvector, the x3 to be as 1, 1, 1, right? So what are the total eigenvectors we got? 3 eigenvectors. x1, that is equal to minus 2, 1, 0, right? x2 to be equal to 0, 1, minus 2, and x3 to be equal to 1, 1, 1. And from these eigenvectors we write the matrix P. Writing this in the column format, minus 2, 1, 0. Writing this in a column format, 0, 0, 1, minus 2, and then 1, 1, 1. This is your matrix P. We have found such matrix P such that the condition should be that P inverse AP should be the diagonal matrix. So when you find the P inverse, you get P inverse to be 1 divided by 8 into, please find this by yourself, minus 3, 2, 1, 1, 2, minus 3, and 2, 4, 2. This is your P inverse. And when you multiply P with the matrix A and then multiplying the resultant matrix with P inverse, you will be getting the diagonal matrix to be 1, 0, 0, 0, 1, 0, and 0, 0, 5. This is your diagonal matrix. Why? Because we are having only the non-zero entries on the diagonal, the main diagonal, and rest of the entries are 0. So this is your diagonal matrix. And because this is the diagonal matrix, that is why the required matrix P is minus 2, 0, 1, 1, 1, 1, 0, minus 2, 1. This is your required matrix P. That is the matrix you got from these eigenvectors, right? Okay, thank you. Stay blessed.